Greetings and salutations, and welcome to a wonderful day of PChem. So far this semester, we've been focusing on applying quantum mechanics to relatively small systems at the atom scale or below. Well, today all of that changes, and we're going to focus in on molecular structure. So this should hopefully let us bring everything we've been talking about together and start talking about systems you actually care about. So, not too surprising, one of the things we're going to want to start by focusing on is how we can use this quantum mechanics to try and determine molecular structure. This is one of the topics I really care about because once we know the structure of a molecule, we know a lot about its reactivity. And not too surprisingly, we're going to do this largely by using the Schrodinger equation. So what we're going to want to first do is use the Schrodinger equation to determine the energy of the electrons in a molecule with a given structure. So if I have a diatomic molecule, atoms A and B, and they have a distance in between them of r, and then I can try and figure out at what position of the electron will I essentially maximize my interactions with each of these atoms, which again depends on its position. And again, this gets a little bit more complex once I move to a multi-electronic system. But one of the problems is that when I do this, I make an approximation, but it's a pretty well-founded one. It's called the Born-Oppenheimer approximation. And this simply states that electrons are much faster than nuclei, which makes sense because they're much lighter. And because of that, I can treat the positions of the nuclei as fixed while the electron kind of moves freely, which again, on a relative movement scale, these two atoms aren't going anywhere quickly. And so I can try and let the electron relax, let it find its lowest energy state with using the fixed positions of the molecule. So doing this, we can minimize the energy of the electron and figure out the subsequent electronic energy. Now, why this is really important is because if I know the electronic energy of each of these atoms, I can then move my atom slightly and find a new electronic energy. Now, if I've got a diatomic molecule, the only way I can move these two atoms relative to each other is by lengthening or shortening this bond. This will look familiar to anyone who's done the Hickel-Dickel lab. So when we do this, what we can generate is a potential energy curve, which essentially says at a given distance of the two atoms, A and B, I'm going to have a certain energy. And lo and behold, because atoms are lazy, they're going to want to obtain the energy at the lowest state, which we know more frequently as the equilibrium bond length. So this is going to be the distance at which I achieve the minimum energy, and of course, this will be the most favored species. Congratulations, you now determined the equilibrium structure of a diatomic molecule. And you can extend this idea to tri or tetraatomics or to larger molecular systems in general. Now, where this is also useful is that if I know the energy at which this species at equilibrium exists relative to infinite internuclear separation, so I take B and I move it way out to infinity, then we can find another useful property, which again is going to be the bond energy. So this is going to be the depth of the well. And so using this, not only can I use quantum mechanics to determine equilibrium molecular structures, I can use it to determine a lot of the properties of reactivity, such as bond strengths, and eventually things like reactivity, equilibrium constants, and transition states, which we've been looking at in lab. So we can then, in order to try and use Schrodinger's equation to follow this general procedure, we have a slight problem, as we have three major key issues of quantum mechanics that we need to solve. The first of which we've already brought up. So this is the idea that we need to determine how nuclear and electronic movement interact. So far, we've only really had to worry about electronic movement because we've only had a single atom. But we can use Born-Oppenheimer, which says that these two movements are going to be separable. I can solve the electronic movement first and then the nuclear movement. So being able to break this problem in two is going to be a huge help, especially because we've already addressed one component of nuclear energy, which is this simple fact that we can also ignore the kinetics of the nucleus and focus on the electron simply because the kinetic energy of the nuclei is so low relative to the kinetic energy of the electrons, which was, again, an important idea we brought up when we first started looking at polyelectronic systems or multi-electron atoms. So being able to focus solely on electronic movement and then worry about optimizing our nuclear structures later is going to be a huge help. The next major thing we're going to need to bring up is how are we going to determine the Hamiltonian for this system, especially when I'm talking about a system with two or more components. So we introduced this idea a little bit when we were talking about a multi-electron atom, and it turns out it gets much worse when we have multiple nuclei. And the reason for this is what's called the three-body problem. When I have three or more components to a system, because it turns out that you actually can't solve a three-body problem exactly, which means we need to make use of approximate methods. So I can get pretty close to the exact energy, but you'll never know exactly what the minimum energy is for a three-body problem. So our general approach or approximate methods are going to focus on one of two major techniques. So either I can solve a single two-body problem, which essentially will be constructed by taking my multi-body problem and then dropping some terms, forgetting about some things, that looks like a two-body problem if I squint real hard. And then I solve this two-body problem. Alternatively, what we can do is take our multi-body problem, our three or four-body problem, and separate it into a series of two-body problems that I can solve exactly, solve each one of those individually, and then bring this to an overall solution. And so taking these two-body problems and turning them to a net solution occurs via one of two methods that we should be fairly familiar with at this point. Either we can keep adding on corrections to our solution from our two-body problem, or solve all of my two-body problems sequentially, one after another, each time optimizing my overall position, improving my electron position a little bit, or improving my nuclear positions a little bit. And I keep doing this until my energy stops changing, or until the system comes to equilibrium. At which point we say, good enough. And sometimes it is, and sometimes it isn't. And trying to figure out when we're in each of these two cases is going to be one of the major features of this chapter. However, we do have one last major problem left. And this is, how do I tackle the wave function? So I need to build up a set of wave functions that can be used to describe an entire molecular system. And as you remember, this was hard enough doing it for a multi-electronic atom, let alone when I'm constructing a molecule out of several atoms. And it turns out that this will be the focus of a large chunk of this chapter. So we are going to be generally following the same approach we did for multi-electronic systems. So what I'm going to do is instead of trying to solve for one entire wave function for the entire system, I'm going to try and build up my wave function out of a series of two electron wave functions that can either be singly or doubly occupied. And then adding these together, I'll get a wave function for the entire molecule. And we're going to try and build these two electronic wave functions or orbitals out of our hydrogenic orbitals. So yes, these are the same orbitals we solved for exactly in the hydrogen atom, and then kind of pushed around and mushed a little bit to get our multi-electronic orbitals. And we're going to take those multi-electronic orbitals, crunch them together a little bit more, and see if I can build a molecule out of it. It's an approach that is both very nice because I know the solutions for my hydrogenic orbitals exactly. So this is a two-body problem I know how to solve. And so I can try and take these two-body problems, add them together, see if I can make a three-body problem out of it. So again, how we take these molecular orbitals and try and mush them a little bit more to solve for a true molecular wave function is going to be one of the true tricks of quantum mechanics. So we're going to start next time by focusing on how I can try and start building up these molecular wave functions. Take care and stay healthy out there.